So the purpose of today is that we can share experience and knowledge about IoT, AI, and metrology used for IoT and AI. We have quite a lot of participants today, and we are very happy to see that. We are also spread out across the world, so if you could just say hi in the chat and maybe give us a quick information about where you're from. So just a hi and then where you're located in the world, that could be really interesting. For today, I will be going through the host of the program, and we'll also give you a brief introduction to what is this workshop all about. Then we will have an introduction to Metrology for IoT by Nikolaos Agianotis, my colleague in Force Technology. And then David Belslevharder from DFM will introduce Metrology for AI. And then we will have a short break. And afterwards, we will have Jakob Conradsen from UPRI talk about how are they using IoT and metrology to ensure COVID-19 vaccines, and what challenges and opportunities has that given them. Then we're going to do an interesting experiment, because I thought we weren't going to be that many for this workshop, but we're going to do a breakout session. So we will try to divide you into smaller groups of people, where you can then discuss in a small group what is actually the purpose or challenges for IoT and AI with respect to metrology, and how do we deal with these. Then we will try to recap with some conclusions from these breakout sessions and discuss them in a plenum. And then I will just briefly describe what are the future activities that we will be focusing on in this project. But just a quick introduction. So I come from Force Technology, and as you can see from our business areas, we are very widely spread on non-destructive testing. We are performing material testings. We are performing calibrations for humidity. We are doing clean air technologies and a specific metrology division. We are about 1,000 employees. We have 9,000 yearly customers and a development budget of about 30 million euros a year. And we are one of the leading international technology consultants. We are also a not-for-profit, independent and impartial organization, what is called as an Approved Technological Service Institute, GTS, based in Denmark. And I come from this small part down here, which is focusing on IoT. So maybe it's worth to note that some of you are attending as experts in metrology, some of you are attending as experts in IoT, some of you are attending as experts in AI. So the purpose of today is sort of try to align some of the stuff that you will be introduced to is very basic on IoT. Some of the stuff will be very basic on metrology, depending on your area of expertise. But it's just to say that we will have an alignment over the years, over this webinar. And maybe just to say that this is a list of all of the reference labs that we have in Denmark, at least, with the different subject fields. So it's mass-related quantities, it's electricity, magnetism, length, thermometry, ionization, radiation, etc., etc. So there's always a large awareness on all of these reference laboratories that we can use. And I think the challenge for many IoT and AI solutions is that they're not aware of this metrology infrastructure that they can utilize. So we also need to figure out how do we help the IoT and AI communities connect with the metrology community to have more interaction and benefit from each other. Just a quick introduction as well to why we are hosting this webinar. So Force Technology and DFM has gotten performance contracts, which is sponsored by the Ministry of Higher Education and Science in Denmark. And this is in relation particularly to two performance contracts. Our joint contract with Metrology for Digitalization and Data Security, where we will focus on digital transformation of society with focus on metrology needs, including time references for data communication and validation of encryption and AI. And then we also have a performance contract, which is Force and institute called Alexander Institute, which is IoT-driven business design, digitalization of companies and society, which is to create the best circumstances to apply and develop IoT-based services by involvement of the IoT ecosystem. So it's just to frame, and these are 4-year contracts, a multi-million kroner funding that we have for this. So we will have ongoing activities for the next 4 years within this area. And the reason why we are calling for this is that the potential of IoT and AI is hard to overlook. So it's estimated that we will have 25 billion IoT devices in 2025 with a gross turnover of about $3 trillion yearly. So it's a huge market opportunity. We start to see this going from having a lot of pilot projects to becoming adopted into society, and gives us an ability to monitor and detect our world in a way that we haven't been able to before. We see that data sets that we get into our data validation investigations. Last year, we had a system with 6 million data points collected over a year. This year, we see systems with 60 million to 90 billion data points collected per year. And that means that we have some very large data sets that we need to have an overview of and figure out how can we ensure that we produce reliable and traceable data. And then we need to identify where are the needs largest for metrology and how can we combine it with outlier detections. I will elaborate on that in a little bit more. So we have large data sets, we have challenges with transparency in AI algorithms, we have need for metadata description. So many IoT systems are just delivering the data they're collecting, but nothing about the uncertainties associated with that data. And that also associated with digital calibration certificates, where they are digitally available or online available. We have a lot of low-cost sensors that are in distributed systems. It's untrained installation professionals and a lack of understanding of definitions for metrology. And then we see that the cost of calibration is often higher than the device costs. So in Force, one of our prior departments, they developed a thermometer or temperature measurement unit, which costs about $1. It was integrated with RFID to be able to report it. But if we needed to calibrate that under traceable conditions, then the additional cost would be approximately $1 per unit. So it was just as much as the chip itself was the calibration cost. So we need to figure out what strategies can we use for these very, very large systems with tens of thousands of devices. How do we ensure, or at least try to ensure, traceable and documented uncertainties in such systems? So just as a basic introduction, IoT and AI systems components. So when we talk about IoT, it's all about having a thing that we give a representation on the internet. So this is a thing that we're trying to monitor and collect some data about. We do that by connecting a device or associating a device to it that has a sensor, an actuator, where we need some analog electronics that can then steer these sensors and actuators. We need to create that in a digital format, so we need A to D converters. We need to give it an ID, so we have traceability back to the device. We need some RF communication typically that can transmit the data and then give it an IP publicly available on the internet through a gateway. Then we have a block, which is a server, which is typically a rule-based engine deciding on what to do with the data. Should it be sent directly to storage or to AI analytics? There are some event triggers if we see higher values than we expect or above thresholds, etc. We need to maybe trigger an event back to the actuator or to other actuators to change the conditions of the system. Then a large part is about device management and device security. So these are also blocks within the server for the IoT system. And we have the connectivity to the outside world. So APIs are the interchange of data to other systems. Apps are where we have the human interfaces. And the World Wide Web is when we need to collect additional data for the system. Additional data sources that can enrich the data set that we're collecting with our sensors and IoT devices. Oh, just as an example where we can put AI and IoT together is automated speed cameras, where we both have a calibrated speed detection unit within this device. So the thing is the car. We can identify the car through the license plate number if we have what is called OCR reading. So we automatically capture the text written on the license plate. And then we associate that with the speed measurement that we are performing. So there's challenges in figuring out what are, of course, the uncertainty of the speed measurement is something which is fairly standardized, so that's normal. But the uncertainty of the license plate registrations, how do we ensure that we perform this correctly? Also, if there's foreign license plates, so have we used that in the training algorithms for the AI, or will that come out with numbers that looks like in Denmark, a Danish format that will then produce wrong license plates. So it's two very different measurement types that is used in such a system, and we need to figure out how can we ensure the highest integrity of the data that we're producing in such a case. And just as a basic introduction to metrology, the fundamental theory of measurement. So we talk about precision, which refers to the closeness of two or more measurements to each other under the same conditions. So it's basically in the plot you see to the right, how close are the dots or measurement points, how closely are they spaced? The second part is the accuracy, which is the closeness of the measurements to the true value. So it is, as we move across the x-axis, we can see that the accuracy is closer to the target in D than it is in C, but also in A, where we have a closer spacing of the measurement points, but it's not as good to the true value that we are trying to collect. And then the last part about this is, of course, traceability, which refers to an unbroken chain of comparisons relating to a measurement to a known standard, so that we can trace it back to a known standard that we see as the reference for the measurement that we're performing. Just to give you an insight to why we are focusing more on this. So last year we did a project which is called IoT anomaly detection. So this was for indoor environment sensors. So it measures a lot of different parameters such as humidity, temperature, and CO2. And here you can see this is a dashboard that we use, that we attach to an IoT system, and then we basically capture all of the data which is available. And if you see the CO2 graphs here, it's hard for you to see the scale out here, but it's 60,000, which is the maximum value in this graph. And this is the data recorded over a year. So you can see that one sensor started to produce quite inaccurate measurements from the beginning of May and onwards. And we can detect in this dashboard what sensor ID is it, so the ID of the number or the device that is transmitting, and then trying to define what is the possible cause. You can say that values up to 65,000 ppms is something that could be used to kill animals or humans. So it's not a realistic value for these cases. So how did it even encounter that we came to this point? So the signal that we see, and I've focused on it here, is like a lot of erratic values going up and down from about 0 to 65,000. But what happens is that when we're trying to look at data captured over a full year, and some of these devices measure it every 5 minutes, then we cannot display all of that data at once. So we need to aggregate over time to do such a performance. If we are omitting the aggregation, then we see that it's a different type of signal that we see. So we can see that the values are going from almost 0 to 65,535 minus a little bit. And then the height that we see with the aggregation is depending on the closeness of these values that are very high. So it becomes like a pulse width modulation decoding, for those of you who are familiar with that, of these signals. So this is another level of detail. Then we did an investigation where we compared some of these CO2 sensors with a reference laboratory result. So in the light blue curve, we have the exposure graph that you can see below. And then on sensor number 2.1, you can see that the light blue curve and the solid darker blue curve actually corresponds quite nicely. And when you see it on the right-hand side, you can see that it's basically plotted as a function where we have the true CO2 value of the calibration facility and the measured value, and it performs a very nicely correlation. When we look at sensor 2.4, which is below, you can see that the levels that the sensor is outputting is systematically lower for this sensor. And then when we come down to a dose of 0 ppm, we have a very high value. And what really happens is that we perform a negative CO2 concentration. So when you look at the linear interpolation, you can see that we have a negative B coefficient. And of course, the system CO2 concentrations can never be negative. So the value for this was an unsigned integer, which means that it cannot produce a negative value. So if it tries to represent that, it becomes an overflow error. For the integer, it's 65,535 minus the value that we have as an offset. So you can say that these are some very harsh outliers that are introduced. And the real problem is actually that this is introduced by what is called ABC, automated baseline calibration of the devices. You that are metrology experts know that that has nothing to do with a calibration. It's an automated adjustment. So it's important to do that differentiation. Somebody's speaking, so please mute yourself. So it's just to highlight that this was one out of 1,000 sensors that we needed to identify through this overview, and then identify the root cause of these large error values in the system. And this leads us a bit to distribution of errors. So many of you who are dealing with metrology are aware that we try to refer our uncertainty budgets back to a normal or Gaussian distribution. And then we have the conversion factors between uniform and U-shape error distributions, such that we can relate it back to the normal distribution. But the challenges that we see in the case before, it is to a tendency a U-shaped, but it's other error sources that we introduce, and we need to figure out a new way of dealing it. If we look to the IT industry, we can, many are using what is called the median absolute deviation, the MAD score, which is basically that you take the median of the median of the data set. So if we have a data set which is 1, 2, 3, 4, 5, 6, 100, the median becomes 4. Then you calculate the deviations between this median and the values. So -3, -2, -1, 0, 1, 2, and 96. Then you perform the absolute deviations of this, which is 0, 1, 1, 2, 2, 3, 96, which produces a MAD score of 2. And if we compare that to the standard deviation of this data set, then it would be 33.8. So when we, and the reason why the IT industry is working with these median absolute deviations is that when you have these large data sets, it's more robust towards outliers. And then we need to figure out how do we identify these outliers and filter them out of the data set, and then use that when we talk about traceability and uncertainties. And just as a last point, a huge challenge that we also see is that IoT is out in the real world. Here you see a transmitted signal being recorded by the base station up here. And it was sent down from the parking lot on the other side. And you can see that we have large dips in the recorded signal strength that we are receiving. And then we have a fairly flat period with some variations, some dips again, and then some periods. And if you look over here, you can see that it's a train which is parked right next to it on the station. So all of these dips, they correspond to when the train is arriving at the station. So sometimes some of these outliers is actually what we are looking for in our data sets. So it has to be very cautious before we filter out the outliers when we talk about the remaining data set and the metrology relating to that. So, as I mentioned in the beginning, this is intended as an interactive workshop. So therefore, we would like for you to also contribute a bit. So therefore, we've created 2 polls to begin with that we would like for you to join us in. So please use a web browser where you can go into menti.com, www.minti.com. And then fill in the code 37062453. And you can use this and you can provide multiple answers. So why is metrology required for your product or services? Or where do you see it if you are a metrology expert? Where is it particularly relevant for IoT? So I can see that it's legislation and quality assurance. We have customer requirements and transfer of custody. So it's to a large extent quality assurance, which is the leader. If you have another application, then please open up. I don't know why voting is closed. That is a mistake. Do we have challenges in voting right now? Oh, we still have more.
I think it's open again.
Good, thank you. So I mean, a lot of this is for us to try to figure out where should we focus our efforts. Should we use our efforts within quality assurance legislation? But I can see it's actually a quite broad representation with quality assurance leading, but then a lot of customer requirements and then legislative requirements as well. I'll keep this open for another minute or so. I can see that we are getting close to a lot of votes. One comment here is please leave this window open as we will also use it later in the session. Good. In respect of time, I will jump to the next. So for IoT, we talk about application domains. Can you indicate what application domain best describes your product or products? So is it within utility, consumer products, education? Wow. Transport and logistics, manufacturing, machinery, food and life science. So this actually gives a really good indication that we are quite broadly represented. If you are in the others category, if you have the time, please input in the chat what categories that would be, so we can also see if there's a need for an additional focus on that. Good. So thank you very much. I will recap on this discussion a little bit later in the session, and then we will come back to it in the conclusion. So this was basically the introduction. for my for this webinar. Let's move on to Nikolaos Agianotis, who will give us an introduction to metrology for IoT. Nikos, will you start to present?
Yes, definitely. So here it is, and I will share my screen. Sorry, some technical problems here. Yes. So, hello everyone. Thanks for attending today's workshop. My presentation will be focused more into IoT and measurements and metrology. And just briefly about myself, I'm Nikos. I'm a hardware engineer, and I'm working in the Department of IoT Data and Services Innovation here at Force Technology in Denmark. And so I will briefly start with some short overview about the metrology. When we talk about metrology, it's all about measurements. So how do we define the uncertainty of our measurements, and what is the methods that we are using it for taking measurements? And I mean, some of the key concepts in metrology, one can say, is the calibration, where we actually try to find a reference between the raw outputs of a measuring device and then some reference, so that we can correlate the output of the measurements to that measurement that we are measuring. And then there is also quite important the concept of metrological traceability. You can see also here on the right-hand side some representation of this concept, where basically you are able to trace back the measurement that you are doing back to some standard, some reference, and along all these steps that are involved in between the field measurements and the ultimate reference. In the beginning, there are some laboratories that do the accreditation, and on each of those steps, there is some uncertainty that is introduced unavoidably in these measurements. So, I mean, if we then focus more on IoT. So one would ask, why is it that is it something special? Is IoT a special case for metrology and measurements? And I mean, yes, somebody would argue that yes, it is, and that there are quite a lot of things that actually differentiate probably an IoT system from a classical or traditional measuring system. So, for example, first of all, in IoT, we have a quite uncontrolled environment. As also Anas showed in his previous slides, the IoT system is deployed outside in the real world, where many things can happen which you can't really control, and you are not sure when and for how long they will happen. For example, like interference from a train, or drops in the temperature, and so on. Then another, you could say, difference is that the users of the system actually are maybe not trained users of an instrument, as it would be in the case of a device that is used for taking measurements in a laboratory or in another industrial setting. And then another differentiating parameter you can say is that in the case of IoT, we have an immense amount of data that is collected, produced by the sensors, and then collected to some online platforms, and that actually creates perhaps also more chances, more alternatives to the approach that one could take, because you have a large pool of data which you can use for approaching the problems that you may face. And then we also have another parameter which is perhaps different from other cases, where the IoT data are used for taking decisions and even taking autonomous decisions by some models, some robots, and so on. And that by itself creates another aspect in this story. So actually, to elaborate a bit more in this, I have here a trend which we see more and more appearing in IoT applications. So we see that IoT systems are deployed out there in the world, but slowly we're starting to get focus on how to build services based on these devices, on these smart devices. And you could say that one of those cases is where we're going to achieve predictive maintenance, right? So we have a smart machine, a smart robot outside in the production hall of some company, and then we're going to build a service where we predict some damage on this machine before it actually happens, because then if we follow the model of happen and then fix, then that creates a lot of additional costs and maybe unnecessary costs for the company. So how do we achieve that? What is the key parameter? And you could say that the data are the key that unlocks this service. And you could see it in different levels. So first of all, we have the raw data that are collected directly from the sensors that are deployed on the machine. And there's those data are then, of course, processed somehow in order to maybe reject outliers or make more sense of what you are measuring. And then in the end, it also is quite common in these cases that you apply some artificial intelligence model. With all this together, then helps in taking decisions or making decisions by itself, and that is what actually closes the loop between the smart device and then in the end the service. And in fact, here you can see that the uncertainties that are introduced in any of those levels here, either on the raw data or on the later processing stages, can heavily influence the final decision. And if in the end you are basing the decision that you are taking in wrong data or in data that are not to be trusted with very high uncertainty and not precise, then the chances that this decision is wrong are increasing. So that gives an idea why in IoT applications, the quality of the data and the trustness of the data should be something that people should focus on, actually. And let's take an example now of a smart city application. Through this, I will try to present you some challenges that people might encounter in such a system, right? So what are the facts that we have in such a case? So we have a huge number of sensors, sensor network that is deployed outside across the city, and mostly those sensors are low cost. So you could have some temperature sensors, you could have some CO2 sensors, you could have some sensors measuring the water flow and so on. Most probably, most of those sensors will also be uncalibrated, and then you will end up with a large amount of data where a large majority of those will come from sensors that are not calibrated. And however, then maybe you will have some of those that are factory adjusted or calibrated, and maybe some of those might have an official traceable calibration, where you could say that this is my reference for the system. And usually in those applications, it is it's a desire that there is some interoperability. So it means that you want to be able to do data fusion from sensors from this part of the city and the other, or from different kinds of sensors. So I mean, this is this is the environment that one would face in such an application. And let's have a look in some of the challenges that may appear in this case. So I mean, first of all, as I said also before, usually there will be a big variety of sensors, different kinds, and if we start talking about fusing the data between those different kinds of sensors, and even from different areas, from different users, from different providers, then when you're not able to say how accurate are those data, and what is the uncertainty of these measurements, then problems start to appear. And then, as Anna's also mentioned before, there will be very often there will be anomalies in those data, and you will also have some measurements that are missing for the one or the other region. And can you say where and why those anomalies happen in the data? That could be due to environmental effects. So, for example, a huge drop in temperature or humidity. That could be something that some people went there and maybe accidentally removed the sensor from where it was measuring. Or it can also be some drift in the operation of the system due to aging or other parameters. And so the point here is that having just the data in the end, it's quite difficult to know if the anomaly that you see comes from the one or the other region. And then another point, perhaps, that is valid to mention here is the fact that we do the calibration, the factory adjustment in some controlled conditions in the lab, and then we send the sensors outside in the field where they are exposed to all kinds of different environmental changes. And is the calibration that we did, the adjustment that we did, valid also in such a case, or the conditions that are present in the field are that severe that bring the sensor out of calibration? Of course, here you could say that an on-site calibration could be a way to go forward, but maybe that's difficult in some cases. For example, if the sensors are in some very difficult to access places in sewage system or the one or the other breeds, for example. So there are many parameters that can make such application difficult. And then there's the point about whether the recurrent calibrations are sustainable. So the concept here is that usually when you do a calibration, this is usually something that you have to repeat every 2, 3, or 1 year. Or maybe you can extend this period of calibration depending on the data that you are having, if you can estimate somehow the uncertainty of the measurements. But I mean, having in mind that you have a large amount of sensors outside in the field, how easy it is to take them out of operation, perhaps, and then ship them to the lab for a new round of calibration. And how economically sustainable is that for your system? Is that something that you can do, that you can afford? And then also comes the point about the low-cost sensors. So I mean, a vast majority of sensors that are applied in IoT systems are targeted in low-cost sensors, where the drift might be larger than other more expensive sensors, or also there is the aspect about the price. So having a fully traceable calibrated sensor might dramatically increase the price of the end price of the product that you are selling. And then we have another point about missing data and how you deal with this. So there are some techniques where you can impute those data depending on maybe similar sensors that are in the proximity of the sensor that you are missing some data. But in that case, what happens with the uncertainty of the measurement? How can you limit somehow and quantify the uncertainty of this imputed missing data? And then one last point is that you have the data that you have gathered, but how do you know which of those sensors, which of those data come from a calibrated sensor? How do you know what is the exact uncertainty of so related to that sensor? And can you access the calibration certificates? Where can you find those? That is something that probably the digital calibration certificates concept might lose, where the certificates might be available as metadata through the measurements. But there's certainly a point that needs some further consideration in an IoT application. And that actually brings me to some examples that I have gathered together, where I will try to show you some challenges that we faced during past projects here at Force Technology in the IoT department. And the first one is a demonstrator that we built for with the purpose of monitoring corrosion in large infrastructures. And here on the right-hand side, you can see some corrosion sensors that Force Technology has, and that are to be mounted on the rebar of the infrastructure. And what we did is that we made a system which is attached to those sensors, takes measurements, and then transmits them wirelessly to some database. And collecting data in such a scenario is something that you can do. You can see here, this is the data that we have collected from a real field deployment of this sensor. And but then the question is, how can I be sure that these measurements that I have from the corrosion, what is there any standard that I can refer to? Probably there's not, and that's a case where what we did, we tried to extensively characterize the sensor by and the system by heavily accelerating the corrosion in a lab environment, and using this system to monitor what are the values that we measure. Then a similar example was when we built a demonstrator for a humidity sensor for a supply chain. So you can see here, this is the sensor, which is printed on a PET foil, and this is connected to some platform for collecting the data. And for example, you can see here some measurements that we have gathered along this experiment. But then comes the question, right? So how can you be sure that this sensor that you have created, is this a humidity that you measure related to the real humidity that you have? And what is the relationship between that? And here you can see a more extensive test that we did after this so using this sensor, where you can see that there are different sensors that behave differently with the same step response. And on this graph here, you can also see that actually the resistance of the sensor changes just by the temperature of the environment. And lastly, we have the same. We have the same CO2 sensor that Anna mentioned before. And here I just wanted to briefly mention that we can see here that there is some drift, right? So there, no, not some drift. I'm sorry. There is some time response. So the step here, the PWM pulse is what we have applied in the environment, and this is the response of the sensor. And you can see that there is some delay, maybe of 10 minutes or more in this response. And then, so that's to say that the sensors that are being used in the IoT applications are also used in a dynamic way. So, what if the sensor is used in a control loop? Will that have an effect, and what is the effect that it will have in the final application? So, I mean, I think that I see that the time is running out. So, I will very briefly go through some conclusions. The point that I wanted to say from all those slides is that having data in IoT applications which you can trust and which you are sure about its uncertainty is something really important. Especially when things come together, so different sensor systems come together, and AI models are being used for making decisions. And there are certainly some challenges which needs to be addressed for using in the end metrology in IoT applications. And that actually brings me to I don't know, Anna, if we have time now for questions or.
Thank you, Nico. I think we will wait with the questions until we have had David's presentation as well.
Then thank you very much for your attention.
Thank you. You can applaud with the buttons up in the top where you can also raise your hand. So David, would you maybe take the scene and present a bit about metrology for AI?
See, that should work. Yes, thank you very much. Yes, my name is David Batslow-Harder, and I am a team leader at DFM, the National Metrology Institute of Denmark. And my presentation is on metrology and artificial intelligence, and it's based on the just published white paper, which is maybe unfortunate for some of you in Danish. Artificial intelligence has come a long way, and it is being increasingly applied in robotics, biology, medicine, autonomous driving, advanced production. We have AlphaGo beating the world champion in the board game Go. We have DeepFold, which can calculate enzyme compositions that is almost imaginable to think of. And all of it is based on the same, pretty much the same fundamental mathematical model, which is inspired by neural networks. So in principle, it's just a model which takes in data and puts out results, decisions, predictions, detections, so forth and so forth. And as Anna said earlier, these things are just increasing in application and so forth. Do we need it in Denmark? McKinsey made a white paper about AI in Denmark, and there was a questionnaire to Danish tech companies, and 75% of them was doing some kind of experimenting with AI. However, when it really comes to applying it, it's about 5% that actually apply artificial intelligence, but we have much larger representations within robotics, big data analysis, and so forth. So the potential is really huge. There's also a Danish national AI strategy, and it has focus points on health, energy and supply chains, agriculture, and transport. So, however, can we trust AI? There's this nice web page called Incident Database, and there is a whole database of incidents where AI is making bad decisions. There's autonomous car kills a pedestrian, trading algorithm causes a market to flash crash, and billions of dollars are transferred between parties. A facial recognition system causes an innocent person to be arrested. So what is going wrong here? One of the key issues is that, as a metrologist, that I would point out is that AI should be reporting its uncertainties, and I will explain why. But first, how does uncertainty relate into neural networks and artificial intelligence? So neural networks are inspired by biology. Neuron takes in input signals, dendrites, and outputs a signal called the axon. There's only one output, and that's similar way that neural networks and deep neural networks are constructed. So I can, which is depicted down here. Still, yet we have some input vector, numbers, pictures, whatever, and some output decision evaluation. So for using it in a computer, it's of course turned into math, and it's just in principle mathematical functions that are calculated and combined in this sort of network. So usually what comes out is a simple values, and only in recent years people have started to look at what we really need is some sort of distributions coming out of the AI, so that we know, oh, this 0.3 value has some large uncertainty. What is the certainty that it can provide? And that's when metrology starts to get interested, because this is some of the core competences we have. So just the workflow in neural networks is that you do some data acquisition, you clean up the data, you separate it into test data and training data, take the training data, and then you iteratively optimize your model. It can be both in self-adjustments and training and reiterating on the architecture of the AI. And then when you're ready, you do a model testing, and if it's acceptable, people will usually deploy the model. So you have to do some estimates of the correctness, and then that's where you have a data set which both has the input and the output in the data set. So you can, for every input, you can assess if the model output fits this data set correctly, and that's what's depicted over here. This is some idea that it has to these data points, and you can see the blue lines here sort of indicates the deviation from the data points. And from that you can calculate an error signal. It can be done in different ways. And while you are training the model, you can monitor this error, and maybe it converges, then you're happy when it's changing sufficiently little, or maybe it has some minimum, and when is it actually optimal then? People often use then the minimum error position, but this can provide problems. So let's just talk about a little bit what people usually do in order to assess the model. The common thing is to look at, okay, we have some data set which takes the input data and output data Y. We make a wonderful model which fits perfectly through these data points, and then yeah, we can see that it resembles. So if we ask to calculate for an X here, then we'll get a value which is well within the data set. So everything looks fine. But if the model is too simple, then you can have areas where you will have a large deviation, and that's, well, then you would know that you would still have to optimize on your model. Maybe you have to increase the complexity of the system. So you do that, and you keep doing that, and then at some point you do it too much. So you get a red line like this, and you have a point like, okay, we try to test what is the response to an output at this X point, and the model will return this value, which is far away from the actual, from the rest of the data set. So that this is just within like the data set that has been, or the data ranges that has been collected for the AI training. But what happens if we, well, so we have a nice fit here, but what if we go beyond the data points, the data set that we have? Will the model that we have built, will it respond correctly out here? Well, that's not really easy to know, is it? So it would be nice if the AI model can tell you what is the certainty that I have out here based on how much training have I, how much data have I had to train on this region, and then you would have some uncertainty margins that would be reported in the output of the AI model. So, as I said, then we're uncertainties. That is the fundamental of metrology. We have control cards testing that the sensor responds correctly. We at the National Metrology Institute, we do complex uncertainty budgets for the high-performing instrumentations that we do, and we make calibration functions which include error estimation for the instrumentation. So let me just now present a little bit about DFM. DFM is the National Metrology Institute. So this was sort of the problem that I put up for now. And now let me explain from where I am. Yes. Since 1875, a lot of countries in the world has joined the Meter Convention, and Denmark joined in 1875. And all countries members who are members of the Meter Convention is obliged to have a National Metrology Institute and to apply SI units. So DFM is appointed by the Danish Safety and Technology Authority to be a National Metrology Institute. And in order to ensure our or to document our measurement quality system, we are accredited by the Danish accreditation organization DANAC, and we are accredited to the ISO standards 17025 and 17034, which is standards for calibration laboratories and reference material production. So DFM is also a GTS institute like Forsted Technology. That's where we are in family. And as such, we provide advanced technology services to Danish companies in form of calibration, testing, validation, and standardization work. And we also do research. So we are a crossover between academia and industry. DFM is 100% owned by the Technical University of Denmark. And we have a staff of 36 people, of which about 28 is PhDs. So doing measurements, that is sort of like the national part of it. There's also an international part of it. So being a National Metrology Institute, we are supporting the realization of the SI system globally. And we do that by collaboration with other national metrology institutes, so PTB in Germany, NPL in England, NIST in the US, and so forth. The collaboration with the other national institutes is in doing research together and in doing comparisons to ensure that we are always measuring the same getting the same measurements results, or at least we know the uncertainties of our measurements. So at DFM, we have our measurement areas in nanoparticles, length, electricity, thermometry, mass, roughness and hold plates, photonics, electrochemistry, acoustics, and nanoscale measurements. The basic of a calibration, the normal calibration, is that you have some reference instrument, and you have a device under test, and you do a comparison measurement between them. This is two thermometers, and they are measuring in the same oil bath, which is set at some temperature. And this is just a thought example. So the device under test may give this result up here, and the reference thermometer is hopefully performing better. So this has a smaller spread here. And then if we put the device under test measurement onto the reference thermometer, we see that it has some larger noise, and it has an offset from the reference thermometer. So we can apply an adjustment. We can do it just by calculation, or we can adjust the settings of the instrument. But if we do the latter, you should do a recalibration after the adjustment. So an example, as Nico Smart mentioned, uncertainties increase down through the traceability chain. So we have in length measurements, we have a helium neon laser, which is our primary standard at DFM. We actually have 3, so we can always compare the 3 of them. And we compare those to the international community through BIPM. So this helium neon laser has a length uncertainty of 0.02 nanometers. So that's great. But then that's not really applicable to most of our customers. So we have to transfer length measurements from the laser to physical objects. And that's done in an interferometer, and that's a laser Michelson interferometer. And when we're doing that, the uncertainty increases significantly by 3 orders of magnitude. So we're at 0.02 micrometers. And then we use our reference standards to calibrate working standards for the industry. And then, oops. I think it should be 0.1 micrometer here, sorry. And then they use their working standards to calibrate calipers and so forth in their industry, and then they might have wind up with 1 micron uncertainty. So that's sort of the unbroken chain of calibrations. If you are interested in knowing more about metrology, we have a free training material at a website called www.metrology.dk, which we have developed over the past 5 years together with Forza Technology. So, okay, so in all of these measurements, in all measurements and calibration, we have to consider uncertainties. So there are the object that you're measuring on, there's the equipment you're measuring with, there's the measurement method, the operator, the environment, and the reference object or the reference system that you're comparing to. And it's kind of interesting that these aspects sort of relates to artificial intelligence again. So calibration and adjustments is sort of like you're training your network. We have for the methods, we have guides on uncertainty measurements, the GUM, and we have standards on how to perform measurements. And in AI, we have algorithms, and also there's certain expectations for how to build some of the the architectures. We could say that in metrology, we often control parameters, whereas in artificial intelligence, we often gain from having the law of large numbers. The law of large numbers could be applied in metrology, but you often lose it pretty quickly because you can't sort of average forever. That probably also applies for artificial intelligence. We have training data sets, which is relatable to traceable reference objects or materials. And so finally, we have the output. And in metrology, we have to report uncertainty, and that provides the confidence and the traceability, which provide the confidence in the measurement. But in AI, we use this big data set. How does it relate to reality? And we had the issue with what is the uncertainties if we go outside the measurement space of the training set and so forth. So that's where we can look. So let's see, at DFM, we have tried to, well, I'll give a case of what we have done at DFM. So at DFM, we have been trying to improve measurement technology using AI. Our case study is in nanostructures, characterization of nanostructures. And these nanostructures are in injection molding processes and roll-to-roll productions. So this is a injection molding machine. It sort of heats a polymer and with high force presses it into this form that is here, and then it releases it and cools down, and then it spits out these nice plastic pieces. And these have some nice shiny effects to them, as you can see on the picture, and that's due to nanostructures. This is a close-up picture using a atomic force microscopy, or SEM. So what we could do is we use these to collect the data sets and to use that data set to train an AI model, and then we want to improve measurement speed in the production. So can we build a system that can do inline measurements? And we have done that using optical scatterometry. So we have a classical method, and that could be AFM, which is quite slow, and it requires technical personnel to measure it. And the alternative method we want to use is optical spectrometry. There's a light source, there's some optics, you shine it through or reflect it from your sample, and you look at the optical spectrum reflected from the, well, it could be a white light source. So from that, we can build a large data set, or we can build a data set which relates. The red lines here are optical spectra, and the dark here represents a nanostructure. So these are different heights and different widths of the wells in the nanostructure. And that's where we can, if we can use this data set and put it into an AI, then we can get, because we do the analysis, or we train the AI ahead of applying it in the production, then we can gain measurement speed. So this is a sort of recap of doing that. We have the this is essentially showing the same. But can we do it? Well, when you have the trained neural network, then you can use that network to measure on an unknown sample, measure the optical spectrum, put that spectrum into the neural network, and then get an assessment of what the nanostructure is. And it's really hard to do it that way, whereas the calculation the other way, if you have an assessment of the nanostructure, so that's the other one here, if you think up of a nanostructure, then it is possible to actually calculate what the expected optical spectrum would be. So this actually shows, so because it's very hard to do measurements, the AFM measurements, it's difficult to collect a large number of samples. And therefore, it would be nice if you can train the model using a digital twin. So that's something that we have also worked on. And this is an example of different structures that we have thought of. And you can just vary the parameter space as you like and see what the outcome of the optical spectrum would be. And then this AI would sort of be able to train itself using this digital twin, because it just has to suggest a nanostructure, and then the digital twin will tell it what the optical spectrum would be.
We have to be a little cautious of time, David.
Yeah, thank you. So, in essence, what we want to do is that we want to go from having just neural networks which just pass around numbers in the network to pass around distributions or uncertainty intervals within the AI, and also to be able to pass input data which has uncertainties. And then then when you do that, you will also be able to look at covariance analysis, and that will should be able to help you interpret the model behavior and improve the model implementation. Just before I end, I just want to say that as a Metrology Institute, we like to do collaborative research projects, and the EU is doing final negotiations for including a metrology research program in the European Horizon Europe, and it is estimated to be 700 million euros over the next 7 years, and 40% of that will go to external partners. So if you are interested in this, you are welcome to contact us. Also, DFM is a member of the MathMat, which is a European network on mathematical and AI digitization challenges within metrology. And just to round up, this is a link to the activity, and these are the activities, essentially what I've just told you, that we have planned for the near future. And down here we have a depiction of the people working on it. And that's concluding my my presentation.
Thank you very much, David. We have a question from Chua, but I think we should maybe do it in the chat. And in respect of time, I would like to transition directly to the presentation from Europe. Sorry. Jacob, are you available to do the presentation?
Just a second.
So Jacob is from UPRI, who are performing this storage compliance as a service, and I'm very happy to have you as a speaker. It's a very interesting case that you can present to us. So go ahead, please.
Thank you very much. Just to give you a brief introduction of who I am, as Anna said, my name is Jacob, and I'm from UPRI. We're a small Danish company out of Copenhagen. And what we do is we do storage compliance as a service. So as a case study on how to use IoT for compliance needs, that's pretty much what I'm going to talk about today, and some of the challenges that we were facing when we've overcome these challenges over the years and that we're constantly trying to improve on. Firstly, just a small introduction to what we do. We do well, often we tend to focus on the hardware, but we do small data loggers like these, which go on Wi-Fi and offer a wireless solution to monitoring temperature, humidity, and those kind of parameters. We have an online system, and we have this whole quality reporting and automated calibration solution in one. So most of our customers are pharma customers, from the GDP segment all the way up to the GMP segments. So our customers are really interested in monitoring medicine, test samples, and other products that require governmental control. Yeah, this is also just a brief slide on what we do. So we're present in everything from fridges and freezers, incubators, up to large storages, and we're really concerned with monitoring temperature, humidity, carbon dioxide, differential pressure, everything that you could kind of imagine in a laboratory or production or storage setting. And just gonna dive right into it. First of all, I think there have been some really great presentations on why traceability is important. But I often get this question from customers or from internal people here. Why is it even important? And I think this image kind of shows it nicely that if we didn't have traceability, we might as well measure all our data in bananas, right? Or apples or whatever. There's really no meaning to why we should correlate what we measure to temperature or length or humidity or whatever if you don't have traceability. So in my mind, it's a violation almost to say that you measure in temperatures of Celsius degrees if you don't have calibration and or traceability through calibration. So that's really what links us together and makes our whatever we measure comparable to others. I think that's a really good point to make. I had a really great, as a small story, I had a really great conversation some years ago with a company that does who do person counters for stores and malls and exhibition halls and whatever. And there's apparently no standard for counting the number of persons walking through a door. So they kind of continuously have to define what is a person. Two people holding hand, is that one person or is it two half persons? A child? How do you define all those things? So they have to start over with every single customer saying, this is how we define a person. I just find that exaggerates the importance of why we have traceability and all the other stuff that was mentioned earlier. Another thing that I would really like to emphasize in this small presentation is we all know the main traceability chain from our SI standards through our national metrology institutes and through our calibrations laboratory down to our measurement devices. But one thing that I often see that's lacking is actually the traceability to the processes and the products that we're storing, for example. Let's take some of our customers. They will often store medicine. We have roughly a third of all Danish pharmacies, and they store medicine. And that's actually where they want to transfer their traceability to their products and their processes. And that's one thing that I think we should all really focus a little more on. We tend to focus a lot on saying now that our sensors, let it be IoT sensors, are now traceably calibrated, but that's of no importance. To be honest, I don't think anyone really cares that a sensor measures correctly. You care about what the sensor measures and how does that transfer to a process or product. And that's really one of the main concerns we're facing in trying to both convey this message to our customers and try to convey the importance of this. Yeah, just briefly as a small story about us, some of them, Anders asked me, what were your main challenges and what are your main challenges in working with IoT sensors in a pharma segment? And I would say that the three largest challenges that we're facing is cloud. It's our business model, how we do it, and I'll get more into detail on that later. And then the traceability of it all. Yeah. First of all, this is if you ever talk to a pharma company who are really highly regulated companies, they at least 5 to 10 years ago, they would often say, we don't do cloud. Not more than that, we don't do cloud. Most of our customers don't, I think, fully understand why they don't do cloud, but they don't do cloud. That has seen a large change, I think, over the years. These companies, I think it's important to remember that these companies are used to wired systems, systems in which everything is, you can kind of follow the wire from the sensor down to the readout and then down to the piece of paper where the plotter is going on. It's really definable, actually. Some of the things that we have had to put in order, I think, has really worked for us in terms of getting these companies to do cloud is transparency. And that also has to do with a later point, which I call definability, which is if we have customers who are really used to having really tangible equipment that they have perhaps themselves calibrated and have had through the hands for a lot of years, it's really hard for them to transition into something in which the structure itself is really complex and new. So what we have done is really to be transparent about how the system works, how everything is calculated, and how everything goes from being a measurement to being a piece of text on a screen or in a report. That's one thing, at least, that has been really high. Something that I've discussed with a lot of colleagues in the field also over the years is really high quality standards. We are an accredited laboratory ourselves. We calibrate all our own most of our own sensors, and really having that high level of quality, even though it's just seen as just another IoT sensor, I think has been really important for us in order to maintain a position in the market. And lastly, this thing I talked about, definability. I'm pretty sure it's not an English word, and I probably don't have a conversion to Danish for that word. But really being able to explain to the customer what is the path of information from the sensor all the way down to the report or wherever they have to define it. As I also talked about earlier, how do you transfer whenever you have a sensor like this that you could pretty much place anywhere, how do you know which products were stored in the same position as this? And I'll get into this more later, but really taking the customer's hand and walking them through what the process is, how the systems are built, and what they should expect of the system, I think has really worked for us. And also another odd thing that I often see is servers, for example. Some customers would like to have on-site servers because it's way more safe than having Amazon to do it, which I find kind of odd that you could have 3 separate server locations around Europe, and that should be less safe than having an old laptop in the basement running all your measurements and keeping them for at least 10 years. But we're seeing that now, and I think we see some of the large service providers also rising to the challenge as well, also in terms of communicating this to clients. Really important. The next thing is the business model, and this requires some explanation as well. I think, as I said before, what we see in the market is often that people tend to buy their own products, calibrate them themselves, and I think this is important and true as well for production equipment. But there's a large portion of measurement devices, or IoT sensors, as you might call it, which you do not need to own. And what we've done is that we've made a business model in which our customers lease our products. They give us an annual fee, and for that, every year they will receive a new sensor, which they switch around, and they'll send the old one back, and we'll have newly calibrated devices. But there are places in which they have always done it the same way, and bringing anything novel into their business is kind of a challenge. I think what we did in terms of trying to circumvent this in some sense is pretty much look at all the compliance issues that our customers have and try to encapsulate that into one service. Also, when we're talking IoT sensors, I think one important thing is to understand that just digitalizing one part of a customer's process is not enough. I think one of the things that the reasons why we have success is that we've looked at the whole suite of challenges that they have. Where does our product fit into our customers' daily processes? And what does that mean to what kind of responsibility we have? And how should it function together with the customer's processes? That's really been a large thing where I think a lot of years ago we went out with the idea that just digitalization, the capture of data was enough, but there are a lot of other things that you need to take into account. The last thing, as I said before, is traceability, and as I said before, there are some pretty straightforward ones, I would say, which is calibration. We are accredited by DANAC to the ISO 17025 standard, and we calibrate our own sensors. That was the easy part, I would say. The other more difficult part is how do you transfer that traceability to processes and products? And another really good question, what is really the uncertainty of transferring from a piece of measurement equipment to a process? The GMP guidelines, which is good manufacturing processes for pharma businesses, and GDP, good distribution practice for distributors of pharma products, have actually been quite good in defining how you should validate a process, both in terms of your measurement equipment and in terms of how you transfer traceability. But I think a lot of systems, and to some extent our own system as well, has really not fully understood how do you make sure that a product is traceable to the same standard that your measurement equipment is. There's a lot of thermal validation when we're talking warehouses, for example, in which you try to define some sort of uncertainty. But this is still really something that I see a great potential in over the next few years. And in terms of I just had the opportunity to add this to my slide, hence the graphics, I'm sorry about that, is the digital calibration certificates. I think we've been very lucky to be been drawn into the Euromed project on digital calibration certificates. But I think it's really something that we're going to see much more of in the coming years, that just saying that a piece of equipment has been calibrated and now that you transfer that calibration to a product or a process is not going to be enough. I think we're going to see companies utilizing both in terms of setting down the process time, but also in terms of hiring the level of security that your products are really monitored through calibrated equipment. I think we're going to see that. And this, I won't even dare to kind of guess on where it's going, but I think digital calibration certificates and digital twins is something we're going to see much more of in the future. Absolutely. Yeah, that was pretty much it that I have. I don't know, I can hear, Anders, that the questions and comments are going to come in the end. So I tried to do it slightly shorter.
I think this is actually a good time to have a bit of questions. So there was one from Adri. Maybe you want to ask the question in person.
Yeah. Hi, Jacob.
Hi.
Morning. Hi, here in Malaysia. So anyway, just a regular question. You mentioned that you work with the pharmaceutical industry. Have you had any experiences?
I have some difficulties hearing what is being said. Anders, can you reply?
Yeah, so I can repeat. So do you have any experiences with energy or oil and gas industries?
That's a really good question. We're primarily focused on the pharma industries and the related industries to pharma industries. So all the way from pharmacies, doctors, hospitals, testing laboratories, and all the way up to pharma producers. So no, I'm sorry, no.
But would you be interested in perhaps working on something new with an energy company?
Well, absolutely. I think we could just write each other after this, maybe, if it's interesting. Absolutely.
I can maybe add to the point that also as one of the services we have a Nordic IoT center where we can do a scan for dedicated storage and temperature services for energy, oil and gas or custom development. So I think it could be a good collaboration to see what is Jacob and Yupri doing. But I think also that a challenge in IoT that it's a benefit to be very sector oriented as well, because then you know a lot of the operational procedures, etc., and then also on the application. So I'm not hindering a collaboration because I think it could be great as well, but it's a big challenge for many IoT companies to defocus on the current route because I mean, what you're already doing with storage compliance as a service to the pharmaceutical industry is a huge business opportunity by itself, and you're doing really, really well. So I think that's really impressive.
Thank you. And I think just to comment on the point about being sector specific, I think that's a really good point, especially within the pharma segment. It's really important that you can show that you've made the right consideration, both during development and operation and calibration and all these activities around, which really emphasizes, I think, how important it is to be aligned with your customers in terms of IoT sensors. The customer does not really, in my view, understand the importance of digitalization if you're not fully there with them in the process. Absolutely.
Exactly. I completely agree. So good comment and good question.
Thank you.
Chu also asked whether it's possible to transfer the standard via cloud remote calibration instead of physically send the sensor to your lab for calibration.
Well, as no, I still have not found a viable what you call remote calibration method. But what we've done actually over the years is, or what that we're currently working on right now, is actually a very small sensor in which we have a digital calibration certificate. So the users will actually be able to keep the main unit, this one, and be able to transfer the sensor itself via mail, or actually right now we're down to a price in which you actually don't need to send it back. You can just, it's a consumable. I think Anders, you talked about that earlier as well, that the sensors are now so cheap that it becomes a consumable rather than being something you have to send forth and back. And that's one of the things we're gonna deploy over this next half year or so.
But you can say that then it challenges you if you have had a device in the field that has been measuring and you don't send it back to you for a verification calibration, then you don't know if that is still a valid measurement. So I think even there we can have an hour-long discussion, and it's a really interesting one.
Absolutely. And I think that really comes down to the risk-based model that we were discussing as well. I'm seeing more and more customers who are willing to do risk-based decisions on these, as the likelihood of a sensor failing without you noticing becomes really low when you have so many monitoring systems. But yeah, hour-long discussion, agreed. Sorry.
But and I can see there's a common. Thank you.
Chua here. Maybe I can add on why I asked that question, because okay, we are based in Malaysia, the oil and gas company here. So every year we have to send flow meter to, for example, Force Technology, for calibration, for custody transfer, which is a very, we say, time consuming, as well as not so a convenience for us, because the downtime of our operation will be affected. So we are thinking to disrupt with the current technology of cloud and IoT. Why not? We simulate the same condition here in Malaysia and connect our signals all the way via cloud to the Force Technology lab, for example. We simulate exactly the flow, the temperature, pressure, whatever condition that you will simulate in your lab, and yeah, we do this transfer calibration. We don't have to remove the meter, we don't have to drain the hydrocarbon, and we are more environmental friendly. I know it's something like I'm in a dream, but why not?
It's certainly something that in situ calibrations, it's also a discussion and a focus area for IoT metrology, and something that I think it's a good comment, sure, that we should look at. So thank you very much for that, and we will try. I mean, you can see it at fire alarm systems where you do verifications on site already on a bi-yearly basis. And there is more of a performance validation where you validate that the calibrations are still more or less precise. In respect of time, I would like that we transition into the next part. So when I mentioned this earlier, that we have to go into menti.com for the polls, then we have some new polls, but where they are open, so you can apply text comments to these. So please go into www.menti.com and then use the same code 37062453. If you still have the browser open, then you can use it. Now, the idea, and this is where it becomes really interesting because we are a lot more people than I planned, is that we would like for you to go into breakout rooms. So that means that you will be divided into groups of 6 to 7 people. I hope that most are available and paying attention. But when you are sent into these breakout rooms, please have a look at these slides. Discuss within the group what are the primary challenges. I will change the question after 5 minutes, and then you will be introduced to a new question. So discuss in the group, introduce yourself to the other people, and try to have some more open discussions. So I will now try to launch the breakout rooms, and while you're in the breakout rooms, I will stop the recording so it will not be recorded for future reference, and then I will restart it when we resume. Being in the group chat and input to these questions. So you can see that we had some questions about how metrology can differentiate your IoT and AI product or service, confidence in the service and characteristics of the product, assuring confidence in the results ahead of competitions, and one I like a lot in many ways, and reproducible measurements. It's some things that we tend to take as given sometimes for some IoT and AI systems, but unfortunately that's not always the case. If we go back to the previous test and validation of AI devices, I think the proposal of creating a catalog for reference projects with good practices is a really good idea. Many different applications is mentioned in the blue: medical diagnostics, traffic control, authenticity tests, artificial vision for speed ticketing, etc. And more qualified rådgivning, so counseling or guidance on how to combine the two. And then the first question, digital twin standards. I'm participating in SC41, which is a subcommittee joined between ISO and IEC, where there's a group which is focusing on IoT and digital twins, where there will be a framework for data sharing and metadata construction. So that will be interesting with respect to that. Something about regulation and dealing with regulation. We've talked about it, about the risk-based calibration intervals, which is relevant in this case. How to extend the calibration period, the uncertainty of the field conditions. In Force, we have previously done what we call mission profiling. Kim Schmidt, who's attending, has been a large part of that, where it is basically to profile the missions that the IoT devices will go into, and then we can use that to also evaluate under which conditions should we perform the calibrations. And there's a lot of ideas to discuss here. I think it's maybe worth also to address the previous polls that we did. So in the beginning, we had the quality assurance, legislation, operational requirements, customer requirements as the large driver, and then the custody transfer, change of ownership, where the risk reduction is a second opinion is less important.
Sorry, very much lower than science and companies.
Can you repeat that, Rodrigo?
Sorry, I was unmuted.
Okay. And then I think also the large distribution of you who has attended, that there's a large focus on utilities, which many of you were in the oil and gas industry, transportation, logistics, and manufacturing, smart cities, and consumer products is a large portion of the pie where we can focus on performing new activities. So maybe just to wrap up a bit, are there any additional comments to what you have discussed in the group sessions? Feel free to speak up. Or chat.
Sure. Is there any plan for future networking with this group of people? Because there are certainly quite a lot of interest in this area, and I suppose there are a lot of useful, I would say, question and answer that we can tack on further to either sharing of information or collaboration, exactly. or initiate a new project or ideas. How do we move forward? Maybe I hope the organizer can form some kind of, I don't know, a platform for us to put all the expertise together and connect. That's my view.
So certainly we have the attendees list for this meeting, where we will take the liberty to keep in touch, and we will invite for future activities. We have not planned any specific yet, but we definitely would like to have you as a following group. We have a good energy and a lot of good discussions here. So we will keep you involved in the future activities that we are performing, and we will definitely do a follow-up session on this meeting. I would expect in 3 months, maybe half a year's time, where we will then recap on what are the experiences so far? Would we need to have more input from you? Are there additional projects that you are working on that we can see in synergy with the activities that we are performing? Thank you very much for that comment, Ju. Any other comments? So I can see that there's a question about the digital twin, and maybe we should elaborate a bit on that on the future. But you can say that the digital twin is more or less a data space which represents the physical object. So you say that you have a physical thing that you try to monitor, and then you build a digital model. And we actually are participating in that standardization activity, and there's two parts of it. There's one which is a simulation model of the functioning of the device, and then there's one which is the static data repository that represents the device.
And that's it was I think I was the one who asked the question on the digital twins. It's the thing that I think you mentioned that you're in a group, a standards group.
Yep.
Is that it? Is it possible for you to extend this and the participation of the group to people like Chua or myself? We're working in the same office. He's my boss, so we are actually really looking forward into sharing experiences and maybe paving new ways to actually do things, as we were discussing in the room earlier with regards to digital twin. Because I was telling them that since there is no physical measure anymore as a standard, I mean the kilo is no longer physical, where it's only looking at Planck's constant and velocity of sound. So these are all actually pushing for digital twins, if you get what I mean. We're talking about perhaps in the future having a virtual master meter, a virtual prover. That's where we're going, and I think we can do it if we put our minds together. I mean, the people at Force, and we have playing fields that you can test, so to speak. So these are actually opportunities for us to move together forwards, I think.
Yeah. And I think that sounds like a really interesting application also of the digital twin. I posted a chat comment, which is a reference to the standardization group where we will be, or I am working with it. I know David is always also involved in activities. And I also like that you ask whether you can interact directly. And I'm thinking about how we can create some kind of community or user space where you can interact with each other and spin ideas also to input to our project, but also to your projects across. When you say that you would like a catalog of good examples of IoT and AI used for metrology, then it could be a really good opportunity for you inputting those to a channel, and then that we sort of collect all of those and combine it into a report, something like that. But for now, feel free to send me an email with any questions or inputs or anything. The email is in the end of the slideshow, and they will be involved quite quickly. I will send out the recording and also the presentations as soon as possible. I think at the latest at the end of this week. Just a few things to wrap up in the end here as well. So one thing that you can do very directly is that we've created 2 white papers within the metrology project. One is about metrology for the Internet of Things. You can see the link on the right here. I will post it. Sorry. There's one here. I can't select it. Sorry. So one for metrology for Internet of Things, and the other one is metrology and artificial intelligence, posted by the DFM. In addition to that, we also have a white paper, also which is in Danish, the future calibration certificates, which is about digital calibration certificates. And then we've also created a guideline, which is about IoT troubleshooting. So that's more into how can you work with troubleshooting and anomaly detection, and how are we working with it in Force. So all of these are publicly available for download, and I will find some more comments or post them in the chats, the links here. So any other last comments? I can see, one second, we had a lot of comments in the chat that I'm trying to catch up with. One second, I'll just post the links, but you can also access them in the presentations once you're done. So yeah, so about engaging with ISO, you can contact your national standardization organization, depending on what country you're from, the national body of the Standardization Institute, and then they can put you in contact with the ISO committee to contribute. That would be very great. I hope to see some of you there as well. Yeah, we could do a network group on LinkedIn. That could be an opportunity. And also digital twin for ultrasonic meters to extend the recall period could also be very interesting. So I think that this is more or less it for now. As I said, we're going to do a lot of future work, and David also mentioned it, mapping of challenges for IoT traceability, uncertainty of raw data in the system, is investigating the uncertainty propagations in algorithms and artificial intelligence, participating in standardization with metadata models for IoT and AI, and digital twins, investigation on how to implement digital calibration certificates specifically for IoT, and creation of a data validation center where we combine metrology with this outlier detection. And as mentioned, comments, recommendations, interest for collaborations are very welcome. So just send me an email and we'll try to distribute it from there. We'll talk about how to create this user community, and then we will get back to you with an email on that. And thank you for the interest. So without further ado, I have a hand from David.
Yeah, I just want to say thank you, Anders, for hosting the workshop today, and also say to everyone that if they found some of our presentation interesting, you're very welcome to contact us. We also have planned to have what do you call it, company cases. So it could also be a potential that you could be the one that we would do a case together with. So
that's a really good comment as well. And thank you, David. I think we have a really good collaboration here, especially with this extended group. So at 16:00 sharp, we are ending this meeting. Thank you very much for attending, and we will be in touch. Thank you very much for today.